Picture this. You're holding a solid, heavy steel gear in your hand. Now, what if I told you that it wasn't made from molten metal, but from a pile of dust? Well, today we're diving into a manufacturing process that sounds like it's straight out of science fiction, but it's happening all around us. I mean, just look at these things. They're intricate, they're heavy-duty, they look like they were hammered out in a forge or cast from a single block of liquid-hot metal. But they weren't. Every single one of them was built from a fine metal powder, and here's the crazy part, without ever being fully melted. So how on earth is that even possible? Let's break it down. All right, here's our game plan. We're going to start with the magic behind the metal dust itself. Then we'll see how it's made, how it gets pressed into shape, and how a blast of heat completely transforms it. And finally, we'll uncover the unique advantages of this incredible technology. The answer to our puzzle has a name: Powder Metallurgy, or PM for short. And, while it feels super futuristic, it's actually an ancient idea that we've just gotten really, really good at. So, what is it exactly? Well, at its core, powder metallurgy is a process where you take these metal powders, you squeeze them really hard into a specific shape, and then you bake that shape in a furnace. And this baking step, it's called sintering, that's where the real magic happens. The little particles all fuse together into a solid piece, all while staying below the metal's melting point. No melting. And this isn't some brand new invention. Seriously. We're talking about a concept that goes all the way back to the ancient Egyptians making iron tools. It was then perfected in the early 1900s to solve a seemingly impossible problem: how to make the tiny tungsten filaments for light bulbs. And today, that same basic idea is used to make parts inside the phone in your pocket and even in the landing gear of airplanes. The whole journey, from a pile of dust to a finished part, it follows these 5 key steps. It all starts with making the powder, and it ends with a finished solid component. So let's jump into that first step. You can't just grind up a chunk of metal and call it a day. Nope. If you want a high-quality final part, you have to start with a perfectly engineered powder. Absolutely everything depends on it. The most common way to make this special powder is a process called atomization. So on the left, you can see how it works. A stream of molten metal gets blasted by these high-pressure jets of water or gas. Bam! It instantly shatters the liquid into zillions of tiny droplets that solidify in midair. And the result, which you can see up close in the micrograph on the right, is this collection of fine, irregular particles, each one ready to become part of something much bigger. But atomization is just one tool in the toolbox. Depending on the metal you're using and the part you need, there are other really clever methods. You can use gases to create these spongy-looking particles, use electricity to get ultra-pure powders, or for some brittle materials, you can literally just crush and grind them up. Okay, so we have our perfect powder. Now it's time to press it into the shape we want. I like to call this the sandcastle phase, and you're about to see exactly why. But hold on, before we press anything, we have to blend. And this isn't just, stirring stuff in a bowl. This is a super precise step that is absolutely critical for the final product's strength. So, why is blending so important? Well, for starters, it lets us create custom alloys by mixing different powders together. It also makes sure all those particles are spread out nice and even, which gives us consistent strength. And finally, we add a tiny bit of lubricant. Think of it like greasing a baking pan. It just helps the powder flow smoothly and keeps it from sticking to the mold. After blending, the powder gets dumped into a die and squeezed under immense pressure. The result is something called a green compact. And this is the sandcastle. It holds its shape just like a sandcastle, but it's incredibly fragile. It has just enough strength that you can handle it carefully, but yeah, it could easily crumble right back into dust. And the density of this green compact? It's a direct result of how hard you squeeze it. Use low pressure, you get a less dense part. But as you crank up that pressure, you force those individual particles closer and closer together, squeezing out all the empty space. That higher density is absolutely crucial for the final strength of the part. This brings us to the most amazing part of the whole process. We've got our fragile little sandcastle part. Now, we have to turn it into solid, functional metal. So here's the million-dollar question. How do you take this delicate green compact and give it the strength to work as a gear or a bearing inside a car engine? The answer isn't more pressure. The answer is sintering. The green compact is placed in a special furnace and heated up to about 70 to 90% of the metal's melting temperature. Now remember, the particles don't actually melt, but something incredible happens. The atoms on the surface of each tiny particle get so energized that they start to migrate, building little bridges across the gaps to their neighbors. They literally fuse together, creating strong metallic bonds and turning that loose powder into a single solid object. This is it. This is the moment the dust truly becomes a drive shaft. So after all that, you might be thinking, why on earth would you bother with all these steps? Why not just melt the metal and pour it into a mold like we've always done? Well, it turns out powder metallurgy has some very distinct and very powerful advantages. PM is amazing at creating really complex shapes with almost zero material waste. They call it net shape forming, which basically means the shape you make is the shape you keep. Compare that to machining, where you start with a big block and just cut away everything you don't need, creating a ton of scrap. PM is also perfect for churning out huge members of identical parts, and this is a big one, it lets you control the tiny pores inside the metal. You can't do that with other methods, and that's how we get amazing things like self-lubricating bearings and specialized metal filters. And we're not just talking about small, simple parts here. These are main bearing caps for a car engine. They have to withstand incredible forces, day in and day out. And they are made efficiently and with incredible strength, using powder metallurgy. It just goes to show this process can compete with old-school forging and casting, even in the toughest applications. And the savings can be just staggering. When the manufacturer of a part for a commercial sprinkler switched from traditional die casting to powder metallurgy, they cut the cost of that one component by a whopping 60%. That's a massive competitive advantage. So from ancient Egyptian tools to modern car engines, powder metallurgy turns a simple idea, pressed dust, into a high-tech manufacturing powerhouse. It really makes you wonder, right? As we learn to create and control powders on an even smaller scale, all the way down to the level of nanopowders, what seemingly impossible materials and technologies are we going to unlock next?